Hello everyone, my name is Aryan and today I'm going to discuss about weak law of large numbers. Okay, so before starting the concept of weak law of large number, firstly I will discuss about convergence in probability. So as we know that in real analysis, the convergence of sequence xn tending to alpha as xn minus alpha is less than a small number. Okay, so similarly when we are talking about the convergence in probability, so now you can see here how we can define the convergence in probability concept here. A sequence of random variable, okay, x1 x2 xn and so on, is said to converge in probability to a constant a if for any epsilon greater than 0. So as in real analysis, we can simply define it xn minus a less than epsilon, but we are talking about the convergence in probability. So now you can see here we are using capital P sign here for the probability things. So if x1 x2 xn is said to be converged in probability to a constant a, then we can write it limit n tending to infinite probability of xn minus a less than epsilon is equal to 1. This is first condition. And second one, limit n tending to infinite probability xn minus a greater than or equal to epsilon, which is equal to 0. Okay, so these are two conditions. If any of these two conditions hold, then we can write xn converge in probability to a as n tending to infinite. Okay, is it clear? That means if any of these two conditions hold, then we can conclude that xn converges to a in probability as n tending to infinite. So this is the uh, structure or the statement of convergence in probability. Okay, so now we have one more thing is known as the Saviccio theorem. So I have mentioned here the statement part of Saviccio theorem. So now you can see here, as an consequence of Saviccio inequality, we have the following theorem on convergence in probability is known as Saviccio theorem. Okay, so statement part is, so now you can see here, if x1 x2 xn is a sequence of random variables, and if mean mu n and standard deviation sigma n of xn exists for all n, and if sigma n tending to 0 as n tending to infinite, then xn minus mu n converges to 0 in probability as n tending to infinite. Is it clear? That means we are considering here x1 x2 xn is a sequence of random variable with mean mu n and standard deviation sigma n of xn. Okay, and mu n and sigma n exist for all n, and if we are considering sigma n tending to 0 as n tending to infinite, it's provided xn minus mu converges to 0 in probability as n tending to infinite. Okay, so this is the statement part. You can simply prove this statement part by using the Saviccio inequality. So now you can see here in next step. Okay, so proof part of Saviccio theorem. So by Saviccio inequality for epsilon greater than 0, we know that this is the first structure of Saviccio inequality. So now we can write it if probability of xn minus mu n greater than or equal to epsilon, which is less than or equal to 1 upon k square. Okay, and as we know that the relationship between epsilon and k is epsilon is equal to k into sigma n. Okay, so now you can write it k is equal to epsilon by sigma n. So in place of 1 upon k square, you can write it sigma n square by epsilon square. So now you can see here probability of xn minus mu n, which is greater than or equal to epsilon, less than or equal to sigma n square upon epsilon square. So sigma n square upon epsilon square tending to 0 as n tending to infinite. Okay, is it clear? That means sigma n square is variance, and if we're taking n tending to infinite, then sigma n square tending to 0, then this becomes 0. Okay, So now we can conclude that xn minus mu n converges to 0 in probability as n tending to infinite, provided sigma n tending to 0 as n tending to infinite. Is it clear? This is the proof part of Chebyshev theorem by using the Chebyshev inequality. Okay, so means xn converges to mu n in probability as n tending to infinite, provided this condition, sigma n tending to 0 as n tending to infinite. So this is the Chebyshev theorem. Okay, so firstly I have mentioned here convergence in probability things, then I have mentioned Chebyshev theorem. Okay, so now come to the main topic, weak law of large number. Okay, so firstly I have mentioned here the statement part of weak law of large number. So now you can see here, let x1 x2 xn is a sequence of random variables and mu n1 mu2 and so on mu n be their respective means. Okay, that means expected value of x1 is mu1, expected value of x2 is mu2 and so on, expected value of xn is mu n. Okay, and let capital Bn is equal to variance of sum of random variables, which is finite. Is it clear? Okay, then probability of average of x1 x2 xn minus average of respective means less than epsilon greater than or equal to 1 minus eta. Is it clear? So that means average value of x1 x2 xn minus average of their respective means less than epsilon, which is greater than or equal to 1 minus eta. So for all n greater than n naught, where epsilon eta are arbitrary small positive number, provided limit n tending to infinite bn upon n square tending to 0. Okay, that means this will hold provided limit n tending to infinite bn upon n square tending to 0. Is it clear? So this is the statement part. So now come to the proof part of weak law of large number. So come to the next step. Okay, so now you can see here proof part of weak law of large number. So by Chebyshev inequality to the random variable x1 plus x2 plus and so on xn upon n. Okay, then we get for any epsilon greater than 0, you can simply define the Chebyshev inequality for this random variable. So probability of random variable minus expected value of given random variable less than epsilon, which is greater than or equal to 1 minus 1 upon k square. So I am writing here bn upon n square into epsilon square, and here I have explained why I am writing this quantity in place of 1 minus k square. Okay, so as we know that epsilon is equal to k sigma, so now you can write it k is equal to epsilon by sigma. Okay, and the right hand side relation is 1 minus 1 upon k square. So now you can put here the value of k square is sigma square upon epsilon square. Okay, and sigma square is what? Variance of this random variable. So take the variance of random variables. Random variable is x1 plus x2 plus and so on xn upon n. So n square come outside. Okay, and this is variance of x1 plus x2 plus and so on xn. And in statement part we have assumed this value is equal to what? Bn. So that's why we are writing here this is equal to bn upon n square. So now in place of sigma square, what we can put here? Bn upon n square. So that's why in equation number 3 you can see here right hand quantity is 1 minus bn upon n square epsilon square. Is it clear? Okay, so now next step is, now you can see here probability of random variable minus respective expectation of these random variables less than epsilon greater than or equal to 1 minus bn upon n square into epsilon square. Is it clear? So for infinitely increasing value of small n, epsilon is arbitrary. We have, or we assume bn upon n square epsilon square tending to 0 as n tending to infinite. Is it clear? So thus having chosen value, chosen two arbitrary small positive number epsilon and eta, number n naught can be found so that inequality bn upon n square epsilon square less than eta will hold for n greater than n naught. Okay, is it clear? That means here two arbitrary small positive number epsilon and eta and number n naught can be found so that this inequality will hold for this value. Okay, so come to the next part. So consequently we shall have probability of random variable x1 plus x2 plus xn upon n minus their respective mean mu1 plus mu2 plus mun upon n less than epsilon greater than or equal to 1 minus eta. Okay, for all n greater than n naught. N naught is epsilon eta. Okay, so now on the basis of this result we can conclude that x n bar converges to mu n bar in probability provided that bn upon n square tending to 0 as n tending to infinite as per our statement part of weak law of large numbers. Okay, so now for the existence of weak law of large number the following condition must hold. As in statement what we have mentioned, mu1 mu2 mu n are their respective means. Okay, that means first condition is what? Expected value of xi exists for all I. Is it clear? And second condition is what? We have mentioned bn is equal to variance of x1 plus x2 plus and so on xn. That means second condition is bn is equal to variance of x1 plus x2 plus and so on xn exist and finite. Okay, this is second condition for existence of weak law of large number. And third one is what? Third one is bn upon n square tending to 0 as n tending to infinite. So for the existence of weak law of large number the following condition must hold. First one is this, second one is this, and third one is this. Okay, so now you can conclude that condition 1 is what? So condition 1 is necessary condition. Okay, without it weak law of large number can't be whole. Is it clear? Okay, so condition second and third are not necessary and condition 3 is only the sufficient condition. Okay, okay, so for existence of weak law of large number we have three criteria or three condition. Okay, so now come to the next thing or next topic, weak law of large number for i.i.d random variables. i.i.d means identically and independently distributed. So if the variables x1, x2, xn are independent and identically distributed means expected value of xi is equal to mu. That means expected value of x1 is equal to mu, expected value of x2 is equal to mu, expected value of xn is equal to mu, means each xi's have the common mean. And similarly variance of xi is equal to sigma square. That means each xi have the same variance sigma square for all I. Is it clear? So this is the concept of i.i.d. Now we can check whether the weak law of large number hold for i.i.d random variable or not. So as we know that we have three criteria for the existence of weak law of large number. So now we can see here expected value of xi exist. So we have mentioned here expected value of xi is equal to mu. That means first condition hold here. Okay, that means expected value of xi exist. And come to the second condition bn. Bn is equal to what? Variance of x1 plus x2 plus and so on plus xn. And we know that x1, x2, xn are independent. So we can write it variance of x1 plus variance of x2 plus and so on variance of xn. And value of variance of x1 is sigma square, variance of x2 is sigma square, and variance of xn is sigma square. So now you can write it n times sigma square, which is finite and exist. Okay, is it clear? So now come to the third condition. Third condition is what? Limit n tending to infinite bn upon n square tends to 0. So now you can see here bn is what? N sigma square upon n square. So n cancel out, resultant is sigma square by n. So now if we take n tending to infinite then this quantity becomes 0. Is it clear? So now you can see here in case of i.i.d random variable, all these three condition holds. So means weak large number hold for the sequence of i.i.d random variable, and we get xn bar converges to mu in probability. That means xn bar converges in probability to mu. Is it clear? Okay, so this is the concept of weak large number for random variables, and second one, weak large number for i.i.d random variables. So we have mainly three conditions. First one is necessary condition, and last one is sufficient condition. So on the basis of these condition, we can conclude that the given problem hold the weak large number or not. Okay, so thank you so much to everyone for watching this video, and in next video I will again join you with a few problem based on weak large number. So thank you so much.